So in this video we will discuss the proof of this theorem. The theorem says that the uniform limit commute with the Riemann integral. More specifically, if fn be a sequence of continuous function on the interval ab, and if fn converges to f uniformly on the interval ab, then the limit and the Riemann integral they commute to each other. Okay. So there is a one line hidden here, so we can write this one as limit of n approaches infinity integration of a to b f of n x dx. We need to prove actually this one equals to integration of a to b limit of n approaches infinity f of nx dx. That means this limit and this integral they commute. The limit and integral they commute. Okay, and since f of n converges to f uniformly, so this means this part means integration of a to b f of x dx, since f of n converges to f uniformly. So we actually need to prove this one equals to, we need to prove this one equals to that one here. Now since f of n converges to f uniformly, so we will use this information, and using that information we will prove it. Now by the definition of uniform convergence, since f of n converges to f, there is a epsilon for the definition of uniform convergence. Now depending on epsilon, we need to prove this one. Now this epsilon can be small or little big, okay, epsilon or epsilon over 2 or epsilon over 3. Now suppose this epsilon is given, and based on that we will prove it. So first we need to assume that let epsilon greater than 0 be given. Why? Because f of n converges to f uniformly, and for that reason we have a epsilon. Okay, how big is that strip? Okay. So epsilon be given. Now by the definition of uniform convergence, we know that since f of n converges to f uniformly, so uniformly on AB, so choose n more or equals to 1, such that we need to choose n more than or equals to 1, because as n grows, here n equals to f of 1, so n equals to 1 here, n equals to 2, n equals to 3, so such that for all n more or than n, and for all x in AB, the difference between f of n and the function, the limit function f of x, the red one, they are less than epsilon, such that absolute value of f of nx minus f of x, this one is less than epsilon. From the definition of uniform convergence, we know this one. Now since this inequality holds for this strip, if we make the strip smaller, then that inequality will also hold. So how we can make that strip, this one smaller? We can divide this one by b minus a, by a positive number b minus a. Okay, why we did that? Because in next step we need that, that's why we did it. Now for all n more or equals to n, so we need to prove this one, when n approaches infinity, this one equals to that one. So we need to prove the difference between this one and that one is less than epsilon. If we prove that, then we will be done. So absolute value of integration of a to b f of nx dx minus this one integration of a to b f of x dx. So from calculus, from integral, properties of integral, we can write this one integration of a to b f of nx minus f of x dx. We can write this one. There is an absolute sign here. And if we use the triangle inequality for integral, so this can be written as less or equals to integration of a to b absolute value of f of nx minus f of x dx. Okay. Now we know that, so this one, the difference between f of nx minus f of x, this one is less than epsilon over b minus a. So it can be written as less than integration of a to b epsilon over b minus a times dx. Okay, because this one is less than epsilon over b minus a. Now since this term is constant, so it can come out of integral sign and we can write epsilon over b minus a. And so we have integration of a to b dx and it is b minus a. So this one and that one they cancel and we will have only epsilon. We have only epsilon. So to cancel b minus a, we actually divide epsilon by b minus a here. So we prove that the difference between this one and that one is less than epsilon. Now since epsilon greater than 0 was arbitrary, since this one arbitrary, so limit of n approaches infinity, integration of a to b f of nx dx would be same as integration of a to b f of x dx. So this completes the proof. Now remember that this theorem is true only when the function f of n, the sequence of function f of n converges to f uniformly. Okay, if the sequence of function f of n converges to f pointwise, I repeat pointwise, then this theorem is not true. It is only true when it converges uniformly, not pointwise. Thanks for watching.